In previous videos, I've been working with this parallel interface bus, and in this last video, I was able to get my primary board or master to really communicate with my secondary, I've been calling it an AV board, or maybe call it a slave board, to the master. I've been able to get that communication working for a parallel interface bus between this microcontroller and this microcontroller. And there are some things that I didn't, really, and probably still don't fully understand on this parallel interface bus or PIB. But I have figured some more things out. I thought I'd share some of those and show what I'm starting to do with some of this. Now, here on my computer, this is a graphic I had shown on one of the earlier videos talking about taking this little board I built and connecting to the SXB from Western Design Center, and really sending over information and how I was treating the master and the slave and making all of that work. Well, as part of that, as I got in here, I went through the sequence of what was happening, but I had talked a little bit about these over here, this PIR or PIRS 2 through 7. And in the documentation, which on my blog, I have a page that I kind of have been using as a reference. It's just this parallel interface bus post that I have put together. But in it, I do have information down here about these register addresses labeled peers, these pins 210 or bits 210. And if I pull this up a little bit larger, these are basically mailboxes. And so when I look at this visual, I can write data from the primary, whether it's these two boards you see here or the boards I'm actually working with, my latest versions. But I can write data over to these mailboxes on the slave. And something I didn't fully understand at the time of this first video was where does PIRS 3 or PIR 3 and 7 come in? They were listed as having the ability to do kind of an auto handshake. And there's hardware support built into the 265 to be a slave, so a PIB slave. And as you configure it, you have an option to say that when I receive data into mailbox number 3, run the interrupt, basically. That's the negotiation or the handshaking. Same with mailbox number 7. And in my reading of this initially, it doesn't tell me enough to really get to that. But as I've played with all of this, I now realize that, okay, I have mailboxes 2, 3, 4, 5, 6, 7. And this page even breaks out these first two kind of together versus the next 4. And they mark them as you have automatic handshake on mailbox 3 and 7. And then up top it says, well, you might use register 3 or mailbox 3 down there to process, codes, opcodes, commands, things like that. Maybe use register 7 for address or data. And in this video, I've actually set up to do some of this. So I'm going to show you that. But here's kind of what my takeaway is I have these mailboxes, and I'll go use this other visual for a second. From the master, I could write into mailbox number 2 a byte of data. Then I could write into mailbox 3 a byte of data. And when I do that, the interrupt is going to fire because of that auto negotiate if I have that turned on. And then I can access both bytes of data. Or I can fill in mailbox 4, 5, 6, and 7. And when I fill in mailbox 7, the interrupt runs, and I know I have those 4 bytes of data I can work with. Or what I'm doing is I've disabled mailbox auto sync on 3, or auto negotiation, and left it enabled for 7. So I can fill in 2, 3, 4, 5, 6, and when I fill in 7, the interrupt will run, and I have up to then 6 bytes of data that I could have sent over from the master to the slave. And I'm setting it up, the way I'm doing it is I am putting a command into the first 2 bytes. So I've got a 16-bit command that I can specify, and then I have 4 bytes of parameter data. Now, I think the intention is over here is you could send a command once, and then maybe you need to stream 16, bytes of data after that. You could send 4, trigger the interrupt, process the 4, or put them into memory on the receiving on the slave side. Send another 4, send another 4, send another 4, all as part of that first command. So you send a command, interrupt, 4 bytes of data, interrupt, 4 bytes of data, interrupt, 4 bytes, interrupt, 4 bytes, interrupt. And that would be giving me my command along with 16 bytes of data to support that command. But in the process, I've gone through 5 interrupts and have to, of course, piece all that back together. So I decided to do something a little bit different. I'm going to use that type of functionality, but I'm going to allow me or the user to send 6 bytes of data and have 1 interrupt to then look at all 6 bytes of data. And when 6 bytes of data isn't enough, what I'm going to actually then leverage is over here on my system, this dual port static RAM. So I had put in a dual port static RAM as dedicated memory between the 2 microcontrollers. So it's not memory. Well, I guess it does show up as just regular static RAM to each of the controllers, but both can write to it, both can read from it. My intention is really the master here might put a whole bunch of information there. Let's just say, it goes out and puts in 16 bytes of data. Then it can submit a command through PIB. The master then can come down, read those 16 bytes of data, and do something with it. And then, of course, the master could then write back into a different piece of memory within that dual port static RAM, whatever the return status is. And I could even have my primary down here monitor that periodically or do something with that return information. Now, let me just kind of demo some of this. I'm going to get out of this visual and set this off to the side for a minute. And I've got these 2 screens up. So one is TeraTerm, that is connected to my secondary AV board, and that's the USB serial. The other is the VGA output up here that I am going to go ahead and capture, and you'll see there on the screen. And I'm going to go ahead and turn on the system. Now, while it's turning on, it's making a bunch of different post beeps and sounds to let me know how things are testing on the way up. My headset will not pick those up. But when this comes up, I'm looking for this LED on both boards. That LED will be lit solid when they're running in their main loop. So this is running in the main loop. This is running in its main loop. And you'll notice over on my PC, the AV board has sent out a string through the serial saying, yep, I'm initialized. It's also now set up to output to my VGA. And so I clear the screen, I put in a little header that just says, yep, dual 265 running at 10 megahertz, and I give a prompt. So now I can come down to this keyboard, which is plugged into the primary board, and do things like type hello world. And you can see that character data comes through. And basically what's happening is I'm processing the PS2 scan code, keyboard scan code, converting it to ASCII code. And then I'm doing a PIB call up to the secondary, the AV board, to say, I want you to print a char, and here's the parameter data of what char I want you to print. Now, I can do other things, though. I can come in here and say that I would like to, well, if I hit escape, that will clear the screen. And you can see there that's cleared. And if I want, I can do things like say, I would like to see rectangles. And you can see that on the VGA output, I'm generating lots of rectangles, and 1,000 of them just got generated. And I'm randomly picking the location, picking the size, and picking the color. All of that's being done from my master, the primary. So it's doing all of that lifting. But once it has it figured out of this is the rectangle I want, it's going to write to the dual port static RAM. Here's the details. So here's my start X and Y. Here's my end X and Y. Here is my color. And actually it does start X, Y, start X, Y, and width and height, and then color. And I send that data across, and then the secondary, the AV board receives that notification. So the primary writes to the static RAM that says, here's all the data, because it's more data than what will fit in 6 parameters. And I'll show you that here in a bit and why. So it's more than 6 bytes of data to define a rectangle. I set that into the static RAM, and then I make a call through PIB and say, draw me a rectangle. And it goes then and comes back to the static RAM, fetches the parameter data, and then does the draw. And then the primary board rotates to the next one, again, creates random data for those rectangles, goes through the whole process again. And you can see that runs pretty fast. And I can actually come in here and type rectangles again. And you'll see it's just continuing to type on the screen where I had left off. But when I press enter, there goes another 1,000 random rectangles. And it's kind of neat when I do that, the way that I've set this up. I won't press enter quite yet, but when I do, this light was going to flicker, as is this one, because they're not in the loop for main as much, because they're doing some processing. So when you see these flickering heavily, that means they're doing some processing outside of the main loop. And also when this is running, you'll see the blue LED for the serial out running. So I'll run this again. And there we go, we're back. So another 1,000 boxes, or rectangles, I should say. So that is all doing that functionality, letting the primary do a bunch of the calculations, storing some parameter data, making a PIB call to the secondary, and then the secondary can retrieve that and then go through all of the VGA processing. So it has to go out, whether I'm printing a char or I'm drawing a rectangle, it's got to do all of that updating of the video RAM. That's these 4 ICs up here. That's all happening up here independently of this board down here. So this board can now go on and do whatever it wants to do next, and keep on working while this one is processing something. If I hit escape, I can clear the screen again, and again I'm back to a clear screen where I can type, not that, I can type rectangles and get more rectangles. So I've done 2 different PIB setups. I've done one, well, I'll show you when I run the commands, where I just submit everything through PIB. It's the command and the parameter data all in basically a PIB with an interrupt on the slave device. Then the second is I wrote a bunch of parameter data to the static RAM, that dual port static RAM, and then I make a call through PIB that's just process this command, and then it fetches all of the parameter data from the dual port static RAM. Pros and cons to both approaches, but the first one is maybe for the simpler commands. The static RAM I'll use for the things that require more parameter data, because it's much more efficient for me to fill in even a kilobyte worth of parameter data and then just make the call, and then it can directly fetch it, versus me having to go through all of the PIB sequencing and sending all of that information. That actually would be a little bit more overhead possibly. So but let me walk through what I have for code here, and again, I will get this posted. So I'm going to try to highlight some things. I doubt I'll be totally comprehensive. I'm sure I'm going to miss something here, but I can kind of go through this. So first of all, on my primary, I'm going to collapse all of these for a second. I did create a new folder. So I've got my primary code folder, the audiovisual board code folder, and now I've made a common. And both of those can then reference and include this file down here. And in this is where I'm starting to define what are the commands. And so these are the commands I've started to build out so far. I've got a print char. That's going to be command 0 and have no parameter data. Then I've got a clear screen. Oh, sorry, I take that back. Print char has ASCII over for parameter 4. The reason I do parameter 4 is parameter 4 ends up being this mailbox 7. And that's where the interrupt will happen. So if I just say I want to fill in mailboxes 2 and 3 with the command, which is 0 and 0, and then I fill in parameter 4, which is mailbox 7, with the ASCII data, that then triggers the interrupt. In the interrupt, I can determine that, yep, you've asked to do a print char, and you've given me the character you want to print. Clear screen doesn't require any parameters. It's just simply command 1. So again, 16-bit command, so it's I got 8 zeros in the high byte, and then just a 1 and 7 zeros in the low byte. But that tells it to do a clear screen. And then I've got to set character color, set draw color, draw me a rectangle, circle, line, pixel. And the only one I've done for implementation down here is the draw rectangle. So I've done the print char, the clear screen, and the draw rectangle. Those are the only 3 I've actually implemented so far. But with the draw rectangle, I kind of am giving myself some notes that says in the dual port static RAM, then these are the pieces of data that I want to store prior to making the call. So I need a start low byte for X, high byte X, low Y, high Y, That's just to tell me this is where you're starting. Now, my screen resolution is 320 by 240, so technically on the Y, I could get by with a single byte. I just wanted to be consistent, though, and have all of these be word in size. So 2 byte X, 2 byte Y, and then width. I have 2 bytes to specify the width and 2 bytes to specify the height. And again, on the height, I technically only need 1 byte because I don't need to go above 256. But I'm building this out in case I go later to a different VGA that supports 640 by 480 as an example, and then I do need these additional pieces of data. And then I specify the color, and 16-bit color is what I'm sending, although my current video card only supports 1 byte of color. So again, I'm sending extra data that technically isn't needed yet, but giving myself some room down the road to improve my video output. And then whether or not I want to fill the rectangle when I draw it, or is it just the outline. And I'll continue to build this out. And, I can have, 64K worth of commands. So I've got lots and lots of commands I could build as time goes by. Now on my primary board, I can get in and I have my operating system code. And in my operating system code, I do have where as you press enter, and this is previous video I've done on this, I can tell when you press enter, and when you press enter, I can then go check. Did you do a clear, a directory, a version, a help, a hello, an app1, or did you type in rectangles? And if you typed in rectangles and pressed enter, then I have a procedure down here that is do rectangles. And I tell it how many rectangles I want, and then I have a loop. And the loop basically says, load up a number and call a procedure that will give me a random number up to this number. So this is a call. I load up A with my maximum value I want for a random. I call this, and it then populates A with that random. And I go store that in my dual port static RAM. And for now, I'm just hard coding it and say, go to the very beginning of my dual port static RAM and store, essentially, this is my start X. And you'll notice that I am, and maybe it's not clear here, but in this code, I am in 16-bit accumulator, so I am storing 2 bytes. So my entire X, the X high byte and low byte, gets stored with this right here with a random value. Then I do the same thing for the random Y. I grab a random value somewhere up to 239, so 0 to 239. I store that in 2 bytes of data. And then I grab a random width somewhere between 5 and 20, a random height between 5 and 20, and then a random color between 0 and 255 or FF hex. And actually, this is probably not very clear. I had decimal above, so I better put 255 here. And so that's going to give me my randomized, where does my rectangle start, what's the randomized size, and what is the randomized color. And then I call a procedure called PIB draw rectangle. And I've kept all my PIB code on the master or the primary in a separate file, but there's a PIB draw rectangle. And that basically says, okay, go out and grab me what I need to know to send over this command. So I say I need to figure out what my command is. And so I go out and I say load up pib command high. And this is just simply a definition that points to the address of this PIRS2 register. So it's just a friendly name. So instead of me having to say PIRS2 to get to the register, I can say here I want to just say PIB CMD high, and that contains the address that is the same as PIRS2. So this is just saying I want to write into mailbox 2, and what I want to write in there is the 2 bytes of the command, and the command is pib cmd draw rectangle. And so pib cmd draw rectangle is a 0004, and so that's what it's storing in here. It's saying, okay, I want to do a draw rectangle, and I'm going to tell it here is the 1 byte of my command, here's the other byte of the command, store that into mailbox 2 and 3. So that's just populating 2 bytes into the mailbox from the master into the slave, so it knows what command I want. I don't need the next three parameters. I left them in here and I commented them out just so I have a consistent structure. But then I fill in the final parameter, which doesn't matter what I send it, but this is what's going to trigger the slave interrupt. So I finally say, okay, don't send param 1, 2, or 3, but send parameter 4, which is mailbox 7. So here's mailboxes 2, 3, and 7. I'm not filling in mailboxes 4, 5, or 6. And then I say send this 0 to mailbox 7. At that point, the slave will do its auto negotiate. It'll run the interrupt. And from my code there, I'll be able to read this information, these two things and that. Now, in a similar way to that on the master, I can also do sending of characters or doing the clearing of the screen. So I have again, this is on the master, I have a PIB print char, very similar in what I just walked through for the rectangle, but this time the command is PIB command print char. So again, over here, that was this one here, command 0000. And then I say that I want to fill in the command, so mailbox 2 and 3. And then for the data, this is just simply going to pull back what I had put on the stack for the character data, which came into this routine, and I had pushed it to the stack. So when I call PIB print char, whatever's in the A register is the char that's going to get printed. I quickly remember it. I mess up, the A register doing some other stuff. I pull it back down here, and then I run that to out to the send PIB to put it in mailbox 7 of the slave. So again, I'm sending the command with the ASCII value. When I do a clear, I'm sending the command, same process here. It's just the command is clear screen. So the clear screen command is a 1. And I put in the 1 here in the first 2 bytes of data, and then I just simply trigger it by putting a 0 or anything into mailbox 7. So that I just tapped in, right to my keyboard processing or operating system that says, okay, if you pressed enter, look, did you type rectangles? If you're just typing normal keys in my normal keyboard handling routine, I just simply said also make a call to this PIB print char to send the same ASCII, not just to my 2 screens on the master, but also to the VGA output on the slave. And then the escape, same thing. So if I hit a key or I hit escape, that processes that. If I typed rectangles and pressed enter, it sends a totally different command. Now that's all from the primary. So then over on the slave, I do have in my system, I have an interrupt set up. And this is just previous work I had done on PIB in an earlier video, but I just have an interrupt so that if the PIB interrupt is ever triggered, so mailbox 7 gets written to, it'll jump to this PIB handler. I have a routine then over in this PIB slave file that is I have initialization, and then I have my interrupt handler. And when it comes into the interrupt handler, the first thing I do is I got to check out what command it is. And for now, I'm only looking at the low byte of the commands. I'm not bothering with the high bytes at the moment. But what I can do then is just say, was it a print char that you asked to do? Was it a clear screen, or was it a draw rectangle? Now, later, I'll have to check both the high byte and low byte. That's not a big deal. For now, it doesn't matter. And until I get to hundreds of commands, it may not ever matter. But if I say that, okay, you did do a print char, then I have a routine called print char. And then that does basically just prints a char out to my VGA. Clear screen does a clear screen and then gives me a new, cursor or caret. And then if I do a rectangle, this was the more complicated one. So, on the print char, when this comes in, I have to read param 4, which is mailbox 7. But I read mailbox 7 to get the ASCII value. And I already knew that it was a print char command because up here I had loaded up the command low. So that was mailbox 2. Let's see. Yes, mailbox 2. So I'm going to go to mailbox 2. I'm going to check for the command. Mailbox 3 would have been the high byte of the command, which I'm ignoring. I then know it was a print char. Print char, I load up mailbox 7 to get me the ASCII value, with a clear screen. I don't need to load up any additional data. All I know is it's a clear screen. I got down to this. I do have to read mailbox 7 though to clear the interrupt, so I do that regardless. Now on a draw rectangle, I have to then go out to my dual port static RAM and read all of this information and then use that to process basically the VGA routine to draw a rectangle. And so that's what this does. I'm doing some output to the serial, and what you actually saw over on the serial, if I bring that back up, as it was drawing every rectangle, I was outputting. This is all the information. So the first 2 bytes that you see here, this is in hex, 006E as an example. That is the start X. And then it would be the start Y, and then it would be the index, and then it'd be the end Y, and then it would be the color. All that information is I'm just debugging out so that as I generate it on the master, I send it to the slave. The slave is now going through all of this code to say, okay, go out to that dual port static RAM, get me the start byte for X, give me the or 2 bytes, same thing for start Y. Grab me the ending location and add to it. And when I say ending location, so start X, and then what's in this parameter down here, this mailbox, was a width of what I want. So I load up the width and then I add it to the start. And then I say, okay, that is my ending that I'm going to fill in for a region for X. I do the same thing for Y. I put in the color, and then I call a routine I've got called fill region in VRAM. In other words, draw a rectangle is what this is doing. And this output over here was just letting me debug. So as it was screaming through this, I was doing all these prints, and that way I could kind of watch this fly by and just see if I've got anything wrong in my calculations. But that's how I then handle this. And then at the end, I just say, get out of here and return things on the stack to a decent state. But that's all over on the slave. So, at a high level, if I go back to the visual here again, I know the board I'm using looks very different than these boards, but it's the same microcontrollers. It's the exact same thing that I'm doing. So from the board on the right, I'm filling in mailbox 2 and 3 with the command. I might be filling in 4, 5, 6 mailboxes with stuff if I need to. And then finally, when I write to mailbox 7, the interrupt triggers. It checks on the slave. Well, which command did you ask for? It reads the parameter data from the other mailbox slots if it's there, or if it knows that, nope, I need to go get this from the static RAM, it runs over to the static RAM and fetches the data. So in the case of my print char and my escape or clear screen, it didn't need to use the static RAM, but for my rectangles, it did, because it was more than what was going to fit in my 4 bytes of available data. If I want a start, an end, a height, a width, and a color, and try to leave those all as 2 byte for future expansion. So I leverage the static RAM to do that. And I think those are the main pieces I've got here. So, on the primary, there's a bunch here. Obviously, I've got a common file where I'm going to try to document what I'm doing as I go, so I know how to remember how to use it myself. The primary, I have things like my PS2 keyboard handler that then turns around and calls PIB primary. I have the operating system that pays attention to the enter key and commands. It calls PIB primary. PIB primary does the bit banging to get it out through the private connection between the 2 microcontrollers. And it might also write to the dual port static RAM. And then my slave up here, it hits the interrupt that is in the main file and then goes over to PIB slave and processes those interrupts and says which command, what parameters, what do I need to get off of the dual port static RAM, and then it executes. And again, the rectangle is the more complicated one that leverages the dual port static RAM for all of this information here, because that doesn't all fit into those 6 mailboxes. So I think this is a kind of a neat example of how I'm going to interconnect between the 2 boards. I have a lot of work to do. You will notice that, let's see if I go back to my primary and let's see, PIB primary. When I go to send rectangles, I did put in a little bit of a delay in here, and that might actually be on my OS. So here's on my OS, I do this rectangles, and I say I want 1,000 rectangles. I wait a few milliseconds between each call. If I take that down to no delay, the master actually writes to the dual port static RAM faster than the VGA output on the secondary card can actually get the drawing done. And so I was finding that it's mid-drawing of a rectangle or starting to, and I go in and I modify or clobber the data with the next rectangle's data. So things like a buffer, so that every time I do a rectangle, it draws it in a new spot in the dual port static RAM and not back to the same spots that I'm writing to. And maybe that makes sense, maybe it doesn't. But what I'm doing right now is putting in a slight delay so that the slave can completely finish processing a rectangle before I try to write to it again from the master. But I think in the future, I can have that be more intelligent. I can buffer and kind of queue up those commands so that the slave can process as it can, as fast as it can. The master doesn't have to worry about timing things for the slave to keep up. It can just pound things into a queue and let the slave deal with it until, of course, I run out of dual port static RAM. And I can't imagine I'm going to do anything that's going to feed it so fast. Maybe when I get into audio sequences, I could do that. I guess we'll see how that goes. But this is hopefully a helpful, overview just to kind of better understand, how is some of this working better with the mailboxes, so this PIRS 2, 3, 4, 5, 6, and 7. Oh, and maybe one thing I should mention, I think I failed to say, when you go to set up the slave, I do have an init. That's where you can tell it if you want it to negotiate on mailbox 3. And so when I come down here, there's this thing called PIB. So this would be your PIB, basically enable register. And this value here says enable PIB and enable the automatic handshake on mailbox 7. This one up here, if I use that value instead, that says enable PIB, automatic handshake on 7, and automatic handshake on mailbox 3. So if you wanted the automatic mailbox, that's how you would set it on for mailbox 3. And then up here, I've got some notes in here, again, coming from the data sheets. But anything that says slave settable, you can configure here in the slave code. If it's master settable, I don't know the purpose of that. That's something that the master has to set. I don't think the 265 has the master capability. So they're saying some master outside of a 265, or you bit bang it, those are set on the master. But if I do slave settable, you see that there's just 4 things. Is it enabled? Is mailbox 3 an automatic handshake? Is mailbox 7 an automatic handshake? And then there's an enable manual handshake from the host. And I've not messed with that one, so I can't explain that one yet, but 3 of these now make sense to me, the enable and then these automatic handshakes for 7 and 3. But that's just by setting this PIB. So I hope this was helpful, especially if any of you, I know it's a long shot that anybody's messing with doing PIB between a pair of 265s, but if you are, hopefully this is helpful. Or if you're going to try to connect it up as a slave to some other type of processor or microcontroller, hopefully this adds a little bit of context to some of the documentation from Western Design Center.